Welcome. In this video, we will discuss about the various sources of sag and its effect and how to evaluate in the real-time environment. So, voltage sag is defined as the reduction in the RMS magnitude of the voltage between 10 percentage to 90 percentage of the rated value, or according to the definition, it is the reduction in the RMS voltage between 0.1 to 0.9 per unit. Okay, and the sag is characterized under two categories based on the duration, how long this voltage magnitude deviation persists. If the sag duration is less than a minute, it is considered as an voltage sag. If the duration is more than a minute, then it is classified under voltage. The duration of voltage sag has a greater significance on the performance of the load equipment, and hence the classification is made. The sources of voltage sags are the switching on of large loads and the system faults, majorly on the unsymmetrical faults. And this fault can happen under two categories. Either it is going to happen on the transmission side, which accounts to 31% of the total fault reported, and on the distribution side, the remaining 69%. So among the distribution side, again, it is further subdivided into two categories. One is the own circuit fault, the other one is fault in parallel circuit. So the own circuit faults accounts to 23%, and the fault in parallel circuits accounts to 46%. And then we have the motor starting sag. So the motor starting sag is nothing but if if you start a large induction motors, it will draw a heavy inrush current at the time of starting, and this heavy inrush current, while flowing through the system impedance, will create a large voltage drop across the system impedance, and hence the terminal voltage of the motor, also the connected loads, will dip to a certain value depending on the magnitude of the starting current drawn by the motor. So the magnitude of starting current is dependent on the power rating of the motor. So, and it is directly proportional. If larger is the size, then the heavy inrush current also going to be more. And it may be caused due to the momentary overload condition in the power system. And you know this, under overload condition, again the current magnitude will be high. If the current magnitude is high, then what happens? This will be reflected back in terms of the increase in the current, will increase the voltage drop across the system reactance. In turn, it will affect the regulation, right? So this is the sources. These are the sources of the voltage sag that can occur in a power system. And it is mandatory to estimate the impact of sag and its severity. Okay, so in order to perform this, we need to consider several parameters or aspects on which the sag the performance is being evaluated. Okay, so in that sense, if you take here, the first thing that comes is you have first we need to determine the number and the characteristics of voltage sag that is going to happen as a result of fault in the transmission system. This is the first thing we need to look into. Okay, and the second category is we have to determine the number and characteristics of the voltage sag that results from faults that occurs in a distribution system. And then the third one is we have to determine the equipment sensitivity to voltage sags. So this will determine the actual performance of the production process based on the voltage sag performance that is calculated under step 1 and step 2. So this is nothing but we need to study the impact of any load under the condition of under voltage. So what is the performance of the system at the rated voltage, and what is the performance of the system at under a voltage condition. And we need to assess what is the minimum voltage with which the system can operate without undergoing any failure or without any degradation in the performance. Okay, so that is what we need to refer as minimum sag right through capability. We'll be discussing on it in the next slide. And based on the performance, we have to map the performance with the economics. Means everything we need to account it in terms of revenue and the money, etc. So that is what we need to do it here now. So with this information, we can effectively evaluate the SAC performance in the system due to the under voltage phenomena. And the next is assessment of the area of vulnerability. So the very first thing, what we need to understand, what we need to assess is what is the minimum voltage that an equipment can withstand without undergoing the mal operation or without any degradation of the performance, and that is referred to the minimum voltage sag right through capability. Okay, and now in this case, what we need to understand here from the area of vulnerability is, let us consider a power system which is shown in the figure, right? So in this figure, it has three feeders connecting three different buses, and you see this A, B, C, D, E, F are the circuit breakers that are being provided in the transmission network for the purpose of protection. And you see to the bus which is connected to the breakers A and F, it is feeding the primary, and from the secondary there are several transmission lines through which the loads are connected. And this 1, 2, 3, 4 are the breakers that are provided in the individual transmission lines for the protection. So I can consider this respectively the transmission line 1, transmission line 2, line 3 and line 4. Okay, and now it can be said that this transformer secondary is parallelly supplying four transmission lines, or four separate feeders. Okay, and so with respect to one, the parallel feeders are 2, 3, 4. Okay, and the voltage sag may happen due to the fault present in the feeder 1 itself, that is the one circuit fault. And suppose if there is a fault in the neighboring feeders like say 2, 3 and 4, in that case also there will be an voltage sag that is observed at this particular bus. Okay, that is the fault voltage sag due to the fault in the parallel feeders. And what is the concept of the area of vulnerability is, if suppose if there is a fault that occurs in feeder 1, this impact of fault, to what extent in the power system it can be observed based on the load whatever it is being connected. Okay, and you can see here it has two region, one is with dark shaded region, the other one is the hatched portion. Okay, this hatched portion contains the shaded area also. Okay, which means that the boundary of the hatched portion is more when compared to that of the shaded portion. This shaded portion is observed for the motor with the conventional contactors, and this hatched portion is observed with the induction motors which are fed from the variable frequency drive. Okay, so there is a greater difference between your ASD and the normal motor which is directly connected to the with the conventional drive system. Okay, so now if you see here a motor which is connected to the any of the bus here, if there is any fault that happens in any of the transmission line, wherever it is been, the effect is felt in the shaded area. In the same case, if you consider the case of the adjustable speed drives, that is your variable frequency drives, in that case it is different. You can observe here now in this case the ASDs are sensitive to fault which are propagated in a very far away distance from its location. So that is what we need to understand the area of vulnerability. Okay. So now, in that case, the concept of area of vulnerability has been developed to evaluate the likelihood of sensitive equipment being subjected to lower than its minimum voltage sag right through capability. Okay, so means that an ASD which is located at this point because of the fault that are happening in feeder 1 is sensitive to the voltage variation here. Let us say in this shaded region, because of the fault, the voltage is dropping up to 80% or 60%. But the voltage in the hatched area can reduce up to 80%. That is up to 80% in the sense from point the voltage can be at this point, that is at breaker B it will be around zero point 0.8 per unit, and breaker A, let us say it is zero point 0.6 per unit. Now even for this point, zero point 0.8 per unit voltage sag is not greater when compared to the zero point 0.6 over here or zero point 0.4 at this point, right? In that case also my ASD is sensitive and it cannot operate well or perform well. So how this is being evaluated? So to support this, we are computing the equipment sensitivity to the sag based on its operational characteristics. So this is the operational characteristics in terms of the rated voltage taken on the y-axis against the time which is taken along the x-axis. Here the time is taken as the integer multiples of cycles. So the cycles in the sense 10 cycle, 15 cycle, 20 cycle, 100 cycle, like that we are considering the duration. So the cycle indicates the time duration of one complete cycle of an AC voltage waveform. So for an example, if I am evaluating this for our Indian supply system where our frequency is 50 hertz, the corresponding time period is 20 millisecond. So here one cycle indicates 20 millisecond. If it is 10 cycle, then it is 200 millisecond. Like this, I will be evaluating. If the frequency is 60 hertz, then the corresponding time period is 16.67 millisecond. So one cycle is equated to 16.67 milliseconds, and accordingly, the 10 cycles is evaluated as 166.7 millisecond. In that way, the calculation will be taken. The time calculation is taken along the x-axis. Okay, and on the y-axis, if you take that, we are considering the percentage voltage. Okay, or in terms of per unit, this is 1 per unit, and here this is the 0 per unit. Or in terms of percentage, 0% to 100%, right? So if you take this graph, it has totally 4 curves in it, 2 solid lines and 2 dotted lines. Okay, the 2 solid lines corresponds to the characteristics of an adjustable speed drive and the characteristics of an conventional motor. Okay, so you can see here, this is the character. This solid line indicates the characteristics of an adjustable speed drive ASD or VFD, and this solid line corresponds to the characteristics of the conventional motor. So what I can say here is the conventional motor can operate even at with 50% of the rated voltage, whereas if you take the adjustable speed drive, it can operate only for the minimum voltage of 90%. If the voltage drops below 90%, the ASD will not function. The ASD will stop. But whereas if you take the conventional motor, if the voltage is dropped less than 50%, then only the motor will stop, or else it will continue to run. This is again for the duration of which is measured again against your cycles, the number of cycles present in your x-axis. Okay, so now what is the this two dotted curves? So one is going to be the CBMA curve, that is CBEMA, Computer Business Equipment Manufacturer Association. Okay, so these are nothing but the manufacturer of computers in short. So these people, they are proposing for the IBM machines, whatever they are manufacturing. So what are the voltage conditions that the machine is subjected to work without any the deviation in its performance? So for that they are representing the percentage of voltage, and the slight modification in this CBMA curve is provided by ITI Council. ITI Council is nothing but the Information Technology Industries Council. So they are providing some discrete value. They just modified this curve to the discrete values and they are provided the curve. This is your ITI curve, Information Technology Industries Council. Okay, so these values are evaluated based on the performance of the their computers and the data centers, whatever they are operating. Okay, and these two curves, that is CBE MA curve and the ITA curve, going to serve as a reference for any system based on which we are going to evaluate the sag right through capability and equipment sensitivity to voltage sag. And now if you see here, how I can estimate the sensitivity of the equipment for the event of under voltage. Now in this case, the under voltage can happen in terms of magnitude, over a period of time. Like that, we have the equipments which are sensitive to only to the magnitude of voltage sag. So for an example, you have that under voltage relays, process controls, motor drive control, and many type of automated machines like your semiconductor manufacturing equipment will come under this category. Means even if the magnitude of voltage, if the voltage sag magnitude is high, even for a very shortest duration of time, immediately these equipments may undergo, or the performance of these equipments will be affected. Okay, and the next category is the equipment which are sensitive to both magnitude and the duration of voltage sag. So in these cases, it's not only the magnitude that governs the performance. The magnitude over a certain duration is going to degrade the performance of such equipments. So the examples are your electronic power supplies like SMPS and the laptop chargers. Means these devices can operate even under low voltage condition. Okay, but if it is subjected to an prolonged under voltage condition, in that cases, the performance of these devices will degrade and hence it will undergo failure. Okay, because, and why this is happening? Because at constant power, it is not going to compromise on its output. This laptop charges and SMPS. But since there is a shortage in the input, what happens is the shortage in input voltage is balanced by the increase in the current. So the increase in the current will lead to overheating of the SMPS and laptop charges, which under over a period of long duration, it will affect the uh, the components that are present in your SMPS and laptop charges. So this will lead to the degradation and then malfunction of these equipments. And then is the equipment sensitive to the characteristics other than the magnitude and duration. So this may be due to the phase angle disturbance, but this is not frequently occurring. And all these things are characterized using your CBE MA curve as the reference. And estimating the sag performance, whatever the performance we are evaluating, that must be quantified in terms of a number, and that must be equated and must be converted into equivalent value of money. Then only we can assess what is the loss that we are incurring because of the under voltage condition. So for that purpose only we have this. So now in this, what we do is we need to rely on the computer programs for running the load flow and the short circuit studies on the given system. So while performing this, we need some minimum set of data like the information on number of feeders, the average feeder length, average feeder reactance, short circuit equivalent reactance at the substation, and the details of the protective equipments and the relay and its corresponding settings. All these things must be provided into the computer program before running this load flow and the short circuit studies. So based on this, we need to plan for the protection, right? So in this one, if you see, the equipment manufacturers should have specified the voltage sag right through capability curves available to their customers so that an initial evaluation of the equipment can be performed by the customers. So based on this evaluation, they can quantify Under this particular voltage, what is the performance and what is the corresponding loss or gain. So like that they can have an they can prepare an analysis chart. And the company procuring new equipment should establish a procedure that rates the importance of the equipment, right? And the equipment should at least be able to ride through the voltage sacks with a minimum of 70 percentage of the rated voltage. And why we need to perform all these things are because if we need a protection, again the cost comes into picture. When we are dealing with the quality, automatically the cost is directly proportional. If it is a higher the quality, higher will be the price. And at the same time, in order to ensure this, how we are going to achieve this? Either we need to provide a local protection, is that sufficient, or we need to have a global protection. If you want to have a global protection, then the cost incurred will be high rather than providing an protection at the lower level. So this is quite an example, a small example I can consider. Inside the house, at different point, we use circuit breakers and also we use fuses. Fuses is for very local protection, and we use the circuit breaker is for the next level. So fuse, you can use it for 1 ampere, 2 ampere, 5 ampere, up to 10 ampere, you can go for it, right? Once the fuse blows out under the abnormal condition, then we have to replace it with a new one. So to avoid this, we go with the circuit breakers. So again, for circuit breaker, you have it 10 ampere, 15 ampere, 25 ampere, up to several kiloampere, the ratings are provided. Accordingly, the cost, as the current rating increases, the cost also will increase. But in case of MCB, in under the abnormal conditions, the MCB will trip, but we can restore it without any replacement of fuse. So that makes the difference between your MCB and the fuse. But if you see the cost wise, fuse is cheap when compared to that of the MCBs, and fuse is going to provide a protection for the equipment level. Okay, so in that case, if you see here at the equipment level, the cost for the protection is less, and whereas at the system level the cost for protection is high. So in this way the hierarchy is going to be there. So we need to decide upon on what basis we can assess and what basis we can evaluate. And in the next case, we need to evaluate the solutions at the end user level. What are the solutions we can proceed, and what are the, on what basis we are going to classify. So we are going to classify the solution level based on the power rating, the kVA rating required for the compensation or the protection. So the protection for small loads means small loads here categorized for the power rating of less than 5 kVA. And we can classify for protection for individual equipments or the group of equipment up to 300 kVA. And we have large group of loads or the whole facilities at the low voltage level, or we can provide protection at the medium voltage level on the supply system, right? So again, this hierarchy only. So this is the my individual loads for which we can provide the protection, or else for the group of load at the low voltage level we can provide the protection, and then at the system level we can find the protection. That is going to be at the large scale. So in that sense, we have the first equipment which is used used as a compensating device for the voltage sag is ferro-resonant transformer. So ferro-resonant transformer, it is commonly referred to CVT, constant voltage transformer. And these are basically 1:1 transformers which are excited in the upper saturation level. So normally if you see the transformer core excitation, it will be just before your saturation level in order to utilize the full magnet material. But whereas in case of CVT, the flux, the operating point of the transformer core is at the saturation levels. The saturation level means whatever is the variation in the voltage, and then the secondary one, the flux of the core remains unaltered. Why? Because it is in a overflowing. Saturation means it is overflowing level. So we can maintain a constant voltage at the secondary. But the operating the transformer under the saturation levels will lead to the disturbance in the input side by introducing current harmonics or the ripples in the primary side of your supply network. So this must be compensated through the compensating winding and the neutralizing winding provided in the secondary of your transformer along with the capacitor, right? So this entire setup is going to provide a compensation for the saturation that is created due to your CVT in the primary level, and also it is going to maintain a constant voltage across the load. So you can observe with the CBE-MA curve of the equipment with and without the ferroresonant transformer. In the case where ferroresonant transformer is not present before the load, the load can perform only up to 80% of the rated voltage which is available at your input. Whereas if I install a ferroresonant transformer, even if the supply voltage reduced up to 30%, reduced to 30% of the rated voltage, this equipment, the secondary voltage will not vary and the equipment will perform without any degradation of the performance. Okay, and this is attractive in case of the constant low power loads. In case of variable load, it is not feasible because of the heavy inrush current that produced in the primary winding, and which is going to cause problems to the primary circuit. Okay, so as an alternative, we can go with the magnetic synthesizer. Okay, the magnetic synthesizer is for the power ratings of 15 kVA to 200 kVA rating, and it is more majorly used for in the process of protecting your large computer systems. Okay, and this is going to be operated under three-phase supply system where the power requirement is quite high, and it is going to perform the same way as that of your CVT. Okay, and here the energy that is available in the supply mains is stored in the capacitive network, okay, in the capacitive energy storage bank. And in case of any sag event that has been observed here, in that case the energy stored in the capacitor is retrieved and it is being synthesized into an AC voltage which is being supplied to the load. Okay, and you can see here this is the CBA MA and this is the CBA MA for a magnetic synthesizer. So with the magnetic synthesizer, then equipment can perform up to the 60% of its rated voltage. So this is what the significance of the magnetic synthesizer. And the next case is your active series compensator. The active series compensator is basically a much more flexible device which is made of the power electronic equipment, and with a simple inductor and a capacitor, it is easy for us, or it is possible for us to regulate the both under voltage and over voltage that is present in your system. And this series compensator is connected in series between your supply and the load through a, either it can be directly connected to the system or through an isolation or series injection transformer it can be connected into the network. So under the normal operating condition, this fast acting switch will be turned on so that the source and it is directly connected to the load. In case of sag event, the fast switch is open, and it will, when the fast switch is open, then this active series compensator will be connected in series to the load and source. So what happens, the net voltage at the output is the voltage across the source plus the voltage across your active series compensator. So V naught is equal to V compensator plus the source voltage Vs. If the source voltage is more, then Vs, this compensator voltage will be negative in order to maintain the voltage to be a constant. If Vs is less than the rated value, then the voltage across the compensator will be positive, so that the net voltage across the load remains constant. And you can see this active series compensator can be synthesized or fabricated for the power rating of from 1 kVA to 5 kVA for the small single phase loads, and it can be up to 2 MVA or larger for the medium voltage systems where we need a voltage regulation. So this circuit is going to add or subtract the voltage signal to the input voltage so that the output voltage remains within the specified tolerance during the disturbance. And this circuit can provide the voltage boosting of up to 50%, which is sufficient for almost all voltage sag conditions that are present in the system. And the next case is the uninterrupted power supply, so which we are more familiar with. The online UPS, offline or standby UPS, and the hybrid UPS are the classification under uninterrupted power supply. An online UPS is nothing but under normal condition also the load is connected to the supply mains through an rectifier followed by an inverter. The output of the rectifier going to charge the battery bank on one side, on the other end it is parallelly it is going to supply your load. So at the output, you have the provision of with a manual bypass switch. We can switch either the output to the inverter or it can be directly connected to the supply mains according to the availability. So under normal operating condition, by default it is configured that the load and is connected to the supply mains through the rectifier and the inverter. In case of power failure, the rectifier will not function, and the battery, whatever the energy stored in the battery, is converted into AC through by the inverter, and it is supplied to the load. Okay, and you see the transfer, the time at for the duration for which the inverter will get activated in this. That is, in no time the inverter will be activated in the case of the disturbances. Okay, so the one disadvantage of this online UPS is the cost incurred will be more. Why? Because as long as the load is connected, the rectifier and the inverter will be under operation always. So when the duty cycle of these devices are more, then the cost of this equipment also will be more, and it requires high uh, expenses. So that's why the cost of online UPS is more. And whereas in case of the standby or offline UPS, under normal operating condition, the line is directly connected to the load. In this manual bypass switch, the online UPS is replaced by an automatic transfer switch. When the line is present, then the load is connected to the supply mains directly under normal operating condition. In case of the line failure or the under voltage event which has been observed at the line end, this automatic transfer switch in no time it will transfer the load from line to the inverter. So in that case the inverter will be into operation, thereby converting the energy stored in the battery bank into the power required to the load. And this is effectively this is cost effective solution where you are having a better voltage and the disruption or deviation occurs only for a shorter duration of time. And the next case is your hybrid UPS. So in the hybrid UPS, it is going to be the combination of your online UPS and offline UPS. And what makes the difference here is instead of this automatic transfer switch, here we are having an ferro-resonant transformer. So the CVT, what we discussed in the very first beginning, it is being used here. So this ferro-resonant transformer is going to when the line voltage under normal or under voltage condition, the power flow will be like line to the ferroresonant transformer to the load. In the case of power failure, the battery bank alone is going to supply, and even whatever the power that is being available, since your ferroresonant transformer can take care of the voltage regulation, even at a very low battery capacity also, you can the load can be supplied. Okay, so this makes your hybrid UPS yeah, much beneficial when compared to cost effective compared to the standby UPS and the online UPS. The next solution is to have an motor generator sets. This is a very classical and old technique, costly, bulkier one also to protect your sensitive load from sag. So in these cases, what we have is this is the load is connected to the generator, and the generator is driven from an motor. The motor is supplied from the supply mains. So for an example, this is from the TNAB, we are getting the supply, and from that supply we are running the motor. This motor is going to act like a prime mover for the generator, and the generator provides a constant voltage according to the load variation. And in case of the power failure in the end, in the line end, to the same shaft there attached a flywheel, which is going to act like an energy storage system. So even in the case if the supply main fails, the energy stored in the flywheel, the kinetic energy stored in the inertia of the flywheel, is used to run the generator at the constant speed for some duration. Okay, so what is the benefit of this? Even if the power goes for a short duration, the energy stored in the flywheel is sufficient to maintain the continuity of the load, voltage to the provided to the load. If you take that semiconductor industry and the glass manufacturing industry, mostly this sort of generation, they have their own generating station which is going to have this setup. Okay, they won't rely on the electricity board because of their power deficit, whatever that we have at the generation level. Okay, so this is what the significant and the of this classical motor generator sets. On the other hand, we have the superconducting magnetic energy storage. So what is the benefit here of the superconducting magnetic energy storage device is, we know that the superconductors, when maintained at a particular temperature, the resistance of the element will become zero. So the system becomes a lossless system. We are going to utilize that property of the material for the energy storage. We are going to use the superconducting magnets. Okay, these are nothing but these are the coils, superconductor coils, which is going to store energy in the form of magnetic field. And in case of the power failure, the energy stored in the magnetic field is converted back into an electrical energy, right, thereby maintaining the supply. Since the losses in this system is zero, I can charge this system in no time. It is possible, and I can charge and recharge, discharge it for any number of times, irrespective of the number of charging cycle. Right? In no time, I can make it. So this is the benefit of your SMES over UPS. Why? Because in UPS, the battery has a limited lifetime. It has limited number of charge and discharge cycles. It needs frequent maintenance. But whereas in case of SMES, it is not like that. And since it is resistance is zero, it is almost instantaneous. And if there is any disturbance that is being observed in the line side, within less than one cycle, you can compensate for the missing voltage. So this is the block diagram which shows the principle of energy storage in a superconducting magnetic system. This is the utility grid, and you can see here this is the load where we need the voltage regulation. In between the source and load, we are having a series injection transformer. So in the secondary of the series injection transformer is connected to your SMES. This is your superconducting magnet, which is fed from the power supply to charge it. And you see, for retrieving this, we are having a regulator control, a voltage regulator, a capacitor bank, which is going to convert this AC to DC. And here we are going to have the DC capacitor bank for filtering. Then you have the DC-DC converter, followed by the breaker, and then to the inverter module. So this inverter module converts the DC voltage available here into the AC. And you see this, since we have 3 power electronic converter, it needs to be continuously monitored and sensed, and accordingly the control has to be taken care. Under the normal operating condition, you can see the power supply will be given to the load through the alternative line, bypassing the series injection transformer. Right? In case of power failure, this bypass line will be opened and the power will be injected through the series injection transformer, and hence thereby maintaining the voltage at the point at the load within a limits. Thank you for the understanding.